Right now, orbiting somewhere above us, there are satellites carrying cameras, sensors, and scientific instruments working on collecting data which we use everywhere in our everyday lives. Weather forecasts, climate measurements, GPS signals, and the list goes on. But all that information has to travel hundreds of kilometers through the vacuum of space, through the atmosphere, through the various sources of electromagnetic interference to be able to reach us here on the ground.
At the heart of this project is one of the most fundamental ideas to modern physics and maths, the cornerstone to information theory, the Shannon-Weaver model. The idea is simple, really, but it describes every communication system ever built, from the internet to Voyager 1, as a pipeline, source to encoding, to channel, to decoding, to output. Our project builds this entire pipeline via computer simulation, then stress tests it. We throw every reasonable type of noise and interference it can have at the signal, measure it quantitatively through a series of analysis and metrics, and then ask the question, what is happening to the signal, and how can we protect it from the possible errors?
The first step to this process is to convert a digital image into an analog radio wave signal. The most common form of modulation used in space communication is BPSK, or binary phase shift keyring. This is a simple form of modulation where a change in a bit is represented by the phase of the signal. Here, we have a wave representing 0, 0, 0, 0. And in order to represent a 1, for example, all you need to do is phase shift this section of the wave by pi, as the atmosphere acts as a filter which only allows radio waves through a certain region. We chose 10 GHz as it is the most commonly used radio frequency for space missions, and can bypass this filter. After this conversion, the wave is then sent through space. When it is received on Earth, a demodulator is then required to convert the signal in the form of a sine wave back to its original binary state. This is done by multiplying the signal with a reference signal of the same frequency, which you can tune into on Earth. And now, by doing some rearranging, we are left with two sinusoidal functions like so. The first of which represents the difference between the phase and input, and the second being a function with double the frequency of the signal. By taking the integral in the time range in which a single bit is represented by, or TB, the function with double the frequency evaluates to 0, as the function is always odd in that period. Whilst the first is a constant which can be used to determine the phase difference between the input and the reference signal. By choosing the reference such as the phase is 0, we can then determine whether the bit is 0 or 1 based on the value of the integral, as when the integral evaluates to a positive value, then the phase must be 0, and hence the bit is 0, and vice versa for when the integral is negative. Practically, this can be achieved without performing using Nyquist's theorem. When we receive a signal and multiply with our reference signal, it is of this form. By graphing out this function, we get this signal. We can then take samples at double the frequency of the signal, as according to Nyquist's theorem, hence at 20 GHz for our output, allowing us to approximate the integral by taking the sum of these samples for each bit period.
Now, for the physical part of the project, we've got the channel, and the noise and interference inherent to it. So we can model the corruption due to the channel with this formula, where yt is a received signal, the xt is a transmitted original input signal, and it's convoluted with an interference function h of t, and a noise t is added onto it at the end.
First is the additive white Gaussian noise, or AWGN for short. This is the unavoidable thermal noise in every electron receiver caused by the random motion of electrons. Therefore, it is present in every single real system and sets the fundamental noise floor. The power of this noise is given by power equals Boltzmann's constant times the temperature and the bandwidth. Second is the impulse noise. These are sudden and violent spikes caused by lightning strikes, solar flares, or cosmic ray impacts. Unlike AWGN, it is rare, but its effects are severe. They cause a lot of destruction.
Up is a multipath interference. When a signal travels from satellite to the ground, it bounces off the ionosphere, off buildings, off terrains, off the road, off people. So there's going to be a lot of different multipath delayed copies that are going to be interfered with each other. So you have the original signal, and you're going to have a sum of all the different paths, other paths that are interfering with the signal. So you're going to have a pseudo attenuation and a delay to every other signal. We then modeled the co-channel interference. In a shared radio spectrum, another transmitter on a frequency similar to our signal may interfere with the signal and be picked up by our receiver. So we're modeling this signal as a sinusoid, once again convoluted with our original signal.
Now that the signal has passed through the channel, we need to quantitatively assess the change. We used 4 complementing metrics, each capturing a different aspect of signal degradation. The mean squared error, or MSE, is the most direct measure. It is very simple, computing the average squared distance between the original and the received signal. So the lower its value, the more accurate our received signal. Secondly, we have the signal-to-noise ratio. This is just a ratio between our input power of our signal and the power of our noise of the signal. So the bigger this value, the less the error, and the smaller the value, the bigger the error. There is also a decibel version of the SNR, which is for when the noise gets big, like exponential. So thirdly, we have the bit error rate. This is a quite self-explanatory metric. It is dividing the number of bits flipped or corrupted by the number of bits transmitted in our signal. This is very particularly useful in assessing whether our error correcting codes are useful.
Now we have something even more sophisticated, the SSIM, Structural Similarity Index Measure, which is more tailored towards images, comparing luminescence, contrast, and structure. For the things that matter in real life, for example, the clarity of a GPS image, the SSIM is a good measure of how useful it is in daily life. So, trying to minimize the effects caused by the channel are a real-life engineering problem that needs to be solved. So this is where the error correction codes come in. They're essentially structured redundancy we're adding to our data. They don't contain any information, but information about our own old data. So if some bits are flipped in our original data, these redundancies will tell us which ones are flipped, and we can therefore fix our data. Right. The Hamming 74 is a simple code that transforms a 4-bit data into a 7-bit data by adding 3 redundancy bits. However, this can only detect errors up to 2 bits and repair up to 1 bit.
Like Hamming, LDPC, which stands for Low Density Parity Checks, is a more complicated but more powerful version of Hamming. It is used from Wi-Fi to satellite communication. LDPC works by imposing parity check equations on transmitted bits. However, there's structural differences, such as the Hamming matrix for LDPC being much larger but more sparse, which means there are a lot more zeros in the matrix. It also functions on a different decoding algorithm called belief propagation algorithm, where the variable node holds a sense of belief of whether it's 0 or 1, and reports this belief to the check node. The check node iterates the probability of the variable node many times until the code word satisfies all the parity checks, and updates the variable node based on its holistic information. The clear advantage of LDPC is that it can correct much more than 1 bit, and detect much more than 2 errors.
Now that we have coded all the necessary tools for our investigation, we now put together 2 main pipelines. One being the one with BPSK, modulation and demodulation. The same Shannon process, but instead of encoding, we are using BPSK for modulation, and then BPSK again for demodulation. And pipeline number 2, we are not using BPSK because it's too robust. We're using some more lossy method of encoding. And then we are going to be implementing error correction while encoding. So we're going to be compressing an image down to a set of integers, and then using those integers, converting into binary, using the binary to implement the LDPC, and then converting it back into integers, and then passing it through the channel as a wave, and then decoding it back into integers, and then putting it back into binary for the decoding of LDPC, and then making it back into integers, and making it back into the image for output. So having built these 2 pipelines, we can therefore investigate, first of all, is BPSK as robust as it's set out to be, by applying the noise to it and seeing how the output is changed through specifically BER, the number of bits flipped, and also through a more lossy function, whether the LDPC can effectively correct the noisy information caused by the channel. Afterwards, we can compare the 2 methods of using the error correction by adding redundancies and using the BPSK, between which one of them is more time efficient, as in the rate, which one of them is more information efficient, as in obviously redundancies being added, and just overall, which one is better for information transmission with more accuracy, and which one is more scalable. So, how good is the BPSK actually? From our data, we can see that in comparison with the control piecewise modulation method, the BPSK outperforms it in every way. For BPSK, the BER returns 0 for physical levels of noise for every single type of noise, while the control is experiencing much more severe effects. This goes to show just how robust the BPSK is. However, it is less information dense compared to similar modulation methods such as the QPSK and the 8BSK, which we can investigate further in the future. And those might be more susceptible to noise, and we can make a further investigation on that as well.
To encode our signal with an error correction LDPC, it's vastly decreased the errors as seen from the metrics and the graphs. However, LDPC is not as efficient as we have to transfer lots of parity bits, which are redundancies. Another challenge we have faced when using LDPC is that it is very slow at decoding message. This is due to not using the most efficient decoding library. So in the future, we wish to use better methods of decoding and possibly even look at different rates at which we encode the message.
The physics that is explored in this project isn't just abstract. It is the reason that we see the rings of Saturn so clearly, and the reason why the Voyager 1 now, over 24 billion kilometers away, can still communicate with Earth. So signal processing isn't just engineering, it's how we see, how we reach beyond our planet. Thank you.